Hi, everyone. My name is Andrei Schwartz. I'm a lecturer in the University of Glasgow School of Engineering and also in the Glasgow Computational Engineering Centre. And thank you, everyone, for joining in. I'm really excited to have so many participants, and I'm even more excited for the hands-on session that's going to be happening in the afternoon after lunch. I appreciate everyone who stated their interest in the hands-on session. And I apologize to those who we were not able to invite because of the limitation of spaces. But like Lucas said, we will share an image of the Docker container used for this hands-on session with everyone a bit later this week. And then everyone would be able to try, and we will be happy to answer any questions later on during this week about that. So like Lucas said in the beginning, lectures for today by Ignatius and myself are introductory. And they are maybe a bit more mathematical rather than application-driven, because we want to give you some preliminaries so that we start from some simpler mathematical setups about mixed problems, so that those can be taken to a more complex problem involving more complex physics, which will be presented by Lukas and Hin tomorrow and on Friday. And so Ignatius took you through the mixed formulation for incompressible elasticity. And I want in this lecture to take it even a bit further and consider thermoelastic problems. But before going there, I want to talk a bit about slightly different flavor about mixed formulations on an example of the Poisson problem. So this is going to be the outline for my talk today. I'm going to just briefly highlight again the reason why we're looking to mixed problems. I think Ignatius covered this, so I think I'm going to skip through this. I'll show this example derivation for the mixed weak form for the Poisson equation, and it's going to be slightly different from the way how it was presented in Ignatius' presentation. So please keep on with me about that. And we're going to look into the special benefits coming out of this formulation. Those are the error indicators, which will drive adaptive refinement, giving a very effective solution for this kind of problems. And after we'll see that, we will look into the actual thermoelastic problem and see how mixed formulation can give benefits in that kind of setup. In particular, we're going to consider a special case of a problem where there's a low regularity to the solution, where a solution has so-called kink. And we'll see how using mixed formulation helps to get better solution, both in terms of temperature, stress, displacement, strain, and so on. Okay, so you have seen already this slide in Ignatius' presentation where we're discussing the benefits of the mixed formulation. And Ignatius, in his talk, focused on the first 2 points, that he was handling incompressibility constraints for the linear elastic problem, with the Poisson coefficient being either very close or equal to 0.5. And also, I think he showed that all the new story which comes in when you introduce a new variable, in this case it was pressure, how it permits you to increase the accuracy of a solution, and then what are the stability issues which come with that. So I, in my presentation, want to focus on the last 2 points. And in the first part of my talk, I'm going to be talking about how the mixed formulation provides embedded error estimators and error indicators. And that's maybe one of the huge benefits of using mixed formulations in the first place, because very cheaply, basically for nothing, you're getting an efficient and reliable error estimators with this formulation. And finally, in the last part of my talk, I'm going to be also touching how using a weaker mixed formulation helps you get a better solution in some special cases where you have like kinks in the solution itself, as I was mentioning before. Okay, so I want to go through this slide again so that we fix the ideas and we use that you're familiar with the notation that we're using. So let me just minimize your faces. Yeah, so we're going to call by L2 the Lebesgue space of the square integrable functions, and this definition also defines the norm, L2 norm. we're going to use the H1 for Sobolev spaces. Those are the functions, also scalar functions, which are square integrable themselves, and also their gradients are square integrable. So we can compute the derivative, at least in the weak Sobolev sense. Then in particular, in my talk, I'm going to be focusing mostly on the last two spaces. So Ignatius was mostly working in the previous presentation with H1 and L2 spaces. Here, I'm going to be looking into also spaces HDiff and HCurl. So HDiff space is the space of vectorial functions. So they have several components depending on the dimension of your space, like the physical space, I mean, each component of those functions is square integrable. And then also in case of HDiff, the divergence of the function itself is square integrable. And in the case of HCurl, the curl is square integrable. And well, as we know, divergence of a vector is a scalar. So divergence of u is an L2, while curl of u, the curl is normally defined in maths as a vector. And indeed, in case of 3D, we will always use it as a vector. But in case of 1D, there is this special notation where we, as I'm going to show on the next slide, we assume that curl is actually a scalar in case of 1D. Sorry, in case of 2D, we say that the curl is a scalar. And why is that? Is like if we just focus on 2D, and most of the things I'm going to show today in my presentation are going to be in 2D. So if you look into the spaces HDiff and HCurl, so this is how, this is just a reminder for you how the divergence operator and the curl operator look like. And divergence operator is, of course, gives you a scalar, and normally curl operator gives you a vector. But if you just think that our space is x, y, x and y, so then for any vector lying in this plane, in this plane, for any vector there, the curl would be along the third axis. So it's always going to be perpendicular. And therefore, as we know that curl is always, we know the direction, it's always perpendicular, we can just look into the scalar value of it and consider the result of the curl operation as a scalar, the scalar value. And why is this so useful? Is because in this case, in 2D, it turns out that the spaces HDiff and HCurl are isomorphic. Why is that? It's because of this formula over here. That if you just look into the formula, into the formulas for computing divergence and computing curl, we can see that the curl of a vector u is nothing but minus divergence of a vector, which is not the u, but u rotated by 90 degrees. Yeah. So so here you have a formula for this 90 degrees rotation, and you can check yourself that the formula in the middle of the slide holds. And it means that if we know divergence, we can always get easily curl of a vector. And also it means that in our implementation, we don't need to implement both HDiff and HCurl bases. We can just implement one of them and get another one by rotation by a right angle. And this is something I'm going to quickly stop on in the slides further down. Okay, but then maybe for some of you, those spaces are a bit new, look a bit exotic and unusual. So just to give a nice physical interpretation, the HDiff space is the space with functions, the normal components of which is continuous across any boundaries inside of the domain. Yeah, so like if you have two parts of the domain, omega 1 and omega 2, gamma is the boundary between them. Then if you consider any HDiff function u, its normal component will not have a jump across the boundary by the definition of the space itself. This comes just from the definition of the space that this property holds. And then it's natural to say that the space is very useful for flow and diffusion problems, because you want your flux to be continuous when it flows from one element to another. And perhaps some of you have heard name Rabier-Thomas elements. So this is the classical example of constructing HDiff space, HDiff-based infinite elements. So now looking into the HCurl, it's similar, but we are saying that the tangential component of H curl functions is continuous across any inner boundary. Yeah. So now it's if you take a function u, and if it's in H curl, then u times the tangent vector does not have a jump when you're going from left-hand side to the right-hand side of the boundary gamma. And that means that such space is natural for magnetic problems, because you want your magnetic field lines to be closed. And the classic example for implementing a base for such space is the finite element called Nedelec elements. Okay, so with these preliminaries, I want to go to the to consider the Poisson problem. So yeah, like I said in the beginning, this is like a building blocks to come to the thermoelastic problem in the end of this presentation. So this is the strong statement of the Poisson problem. We have U, which is scalar field, and has to satisfy this equation over here. And we're going to consider the case when U is equal to 0 everywhere on the boundary. So we have a Dirichlet boundary condition everywhere on the boundary of the domain. We're going to look first into the standard weak form for this case. So we know what to do. We multiply the first equation by test functions and integrate by parts. And from the integration by parts, we get the boundary term. And this boundary term vanishes because we have the Dirichlet boundary condition, and the information that we have a fixed field on the boundary is manifested in the space for the test function delta U. We call this essential boundary condition. So what I want to note here is that in the standard weak form, Dirichlet boundary condition on the field itself is manifested in the weak form as essential boundary condition. And then we are looking for the function in H1 space and Sobolev space, because we have a gradient of U, which would satisfy this weak form. Okay, now let's look into the mixed weak form. And this mixed weak form is going to be slightly different from what Ignatius was presenting, because here we will not just add a new additional auxiliary variable. We will change the space for the initial field U, for our primary field U. Yeah, so it will not be in H1 anymore. But so first we introduce a new variable. This is always a must-do step in the mixed problems, that you need to start with a new variable. So here, new variable is flux Q, and we define it as the gradient of U. For the like in this case, for the Poisson problem, it's as simple as that. When we're going to get to the thermal problems, of course, it's going to be flux equals to minus K W, where K is the conductivity to state the Fourier law. And then we have the continuity equation or the Poisson equation itself for the flux Q, and we still have the Dirichlet boundary condition on the remaining on the boundary of the whole domain. Okay, so we have now two equations that we need to solve. So we're going to multiply them both by test function, and we'll integrate by parts. And we multiply the first equation by virtual text function for the field Q, and we multiply the second equation by the virtual test function for the field Q. Then we integrate by parts the term highlighted in a box. It will also give us the boundary integral. And here a very interesting thing happens, because like what do we do with this term? Well, we can do something, because we know that U equals to 0 on the boundary. But previously, in the classical standard weak form, we had the delta U is equal on the boundary, and therefore the boundary term vanished. Here, it's not delta U, it's U itself, which is equal to 0 on the boundary. And therefore, we can say in this case that the Dirichlet boundary condition is manifested in the weak form as the natural boundary condition. And this is not a mistake. Usually we are accustomed to the fact that Dirichlet boundary conditions become essential and Neumann boundary conditions become natural, but this is not the case for the mixed weak formulation that we are discussing over here. Those things are swapped. And acknowledging this, we arrive at this following formulation, where we have the weak form for the flux Q in the space HDF. because we have a divergence operator acting on Q. So to be able to solve this properly, we need Q's to be in HDiff so that the divergence of Q would be square integrable. But you can notice that U doesn't have any derivative operators. There is no nabla U anywhere in these two equations, and therefore U is in L2, and that means that we reduced the regularity for our primary field. And that's the kind of mixed problems that I want to be talking about today. So please notice the differences which are coming in with this formulation. Yeah, so to sum up, we introduced a new variable for the flux, and we end up with a form where this we are searching for this new field Q, a vector field Q in HDiff space. And we are still searching for the primary field U, but now in L2 space. And there are two equations which need to be fulfilled. And this is the point where the local error indicators come up, and global error indicators as well. So, so perhaps I'm sure some of you have heard about the error indicators and error estimators. And maybe one of the most well-known error estimator is the Zenkiewicz-Zhu error estimator. But the estimators defined like that, they usually require to do some post-processing on the solution, to apply some patches on the elements and this kind of things. Here, I'm talking about something much more simple. I don't need to do any post-processing. Is that if I solve this problem over here, all I need to do is to compute the difference between the gradient of U and Q. And that would give me a pretty good estimate of the actual finite element error that I'm getting. Yeah, so like normally we're talking about the finite element error as the difference between the approximated solution and the exact solution. And here I'm saying that this local error indicator or the global error indicator, which is the sum up of this value of this indicator from all the elements across the domain, the value of this indicator will be something very close to the difference between the solution and between the finite element solution and the exact solution. And here probably you would want to ask me a question of how come that I am writing here gradient of U if we said that the U is in L2. So it's a crime to compute a gradient of a function which is not supposed to have a gradient. Well, my answer to this is that we do this a posteriori. We do this after computing the solution, after solving the problem. It would be a crime to consider the field U in L2 and have nabla U, gradient of U, somewhere in our equations. That would be a crime. But since in finite elements we work with the polynomial approximations, polynomial bases, nothing stops us from computing gradient of this polynomial approximation on any given element after we solve the problem. Okay. So this is what I wanted to present. And then now let's just consider a simple 2D problem. And this is going to be the Poisson equation on a 2D square domain. And we're going to construct the problem for a given analytical solution having this shape. So it's equal to 0 on the boundaries. And it has a sharp rise in the center of the domain such that we have this ring where the magnitude of the gradients of the exact solution is very high. And then we can compute the right-hand side. And now we can solve this problem for UH, for the approximate solution, and compare it to the exact solution. I'm not going to go very much into detail in showing the code. I just wanted to stop at a few main points in the implementation, just to give you an idea of how we are doing that. Because in general, if you come from the experience of using commercial codes, finite element codes, things that we are discussing is not possible over there. Like you cannot change the definition of the spaces, you cannot easily change the orders and those kind of things. But maybe this is the biggest strength of our code often, that we can easily play with the spaces, bases, orders, and so on and so forth. So I just wanted to show you what does it mean when I say that we change the space in terms of the change of the code. Yeah. So here I want to use the field U, which is in L2 space. So this is all the only command that I need to give in the code. I need to put in the code to add the field like this. So I define the name of the field, I define the space, and also I define something which we call base. So base is just the recipe for constructing polynomials for approximating function in the space. And we can use different bases. Like, for example, this one is called Ainsworth-Legendre because it's taken from the paper of Mark Ainsworth, and it uses Legendre polynomials. And this one, number one at the end of this function is saying that we're going to need one coefficient per each scalar-based function because we're approximating a scalar field. So in the same way, we're going to add the field Q. And here, as you remember, like a few slides back, I was saying that hdiff and hcurl are isomorphic in 2D. So we don't need to implement both bases. And that's why we didn't implement the hdiff base for 2D. We implemented hcurl, and then we're going to just rotate this base later on in the code. I will show you an operator which is doing that. So everything is consistent in this regard. We are approximating hdiff, but it's just easier for us to construct the base for hcurl. We can use, as you can see, we can use here different polynomial bases. It turns out for different element types, different bases can be more optimal than others. So that we can play with those things. And I also noticed that we just need one coefficient for our for each base function approximating our flux, because the base functions are vectorial themselves. Yeah. So flux is a vector, but the base for hcurl and hdiff is itself a vector. Therefore, we just need one coefficient per each base function. And then it's very easy for us to set up the orders. So here the user will choose the order, and those of you who will be in the hands-on sessions in the afternoon will play with those things that the user can change the order. It can be anything in some reasonable limits. We can discuss those limits later on. But here I can just choose the order P for the for the field U, and that's mistake. This is of course for field U in L2, and I need to choose one order higher for the space Q to satisfy instability conditions in the very similar way applied here compared to what Ignatius presented in the previous lecture. Okay, and just to give you an idea how those functions look like, what does this all mean? All those hdiff and L2 bases. So we're going to show here how they look for different orders. When we start with p equals to 0, if we look into the scalar-based functions in the for the L2 space of the order 0, it's just one function for this square quadrilateral domain, which is equal to constant, well, basically equal to 1. That's L2 scalar-based function of order 0. So if our U is in L2, our Q has to be in hdiff. And then if it's order P for U, it has to be order P plus 1 for Q, as I just presented on the previous slide. So for order 1, we have 4 vectorial base functions. Okay? You can see they're like in 4 directions for 4 sides of our quad. Now, when we increase the order, when p equals to 1, we have 3 scalar base functions in L2 and 8 vectorial base functions in hdiff for order 2. And so forth. We can continue increasing p and continue building this hierarchy of the base functions for L2 base and for hdiff base, and they're all going to be consistent. We're going to have the right number of functions that enforces the stability conditions in the sense that Ignatius presented. Okay, so we talked about this new mixed formulation that I showed to you with 2 equations instead of 1, and I wanted to show you briefly how this manifests itself in the code. Again, we try to develop the code that trying to play with those kind of things, trying to implement the new formulations is as easy as it can be. So, but first of all, something I promised and mentioned before is that we need to do transformation from hcurl to hdiff. So here is a function which would do that. And in the following, in this function, I want to show you how the different terms in our system of equations is being manifested. So for this diagonal term with the HDIF components, we just need to set up this operator shown on the left. Something we're going to be hearing recurring in our presentations today, tomorrow, and on Friday is that we are using this idea of operators, which are being pushed to pipelines, and then those pipelines are executed for all elements in the all the finite elements in the domain, in the mesh. So if I push this operator first for transforming HQL to HDIF, and then this three operators over here for computing parts of my system of equations, I know that later on, all those operators will be executed for all elements in the domain. We call this a pipeline. If you're familiar with the Para view, there's the same logic of naming things here, that we have a pipeline. In the Para view, it's called pipeline of filters. We call it pipeline of operators, which operate on all the elements in the mesh. So in this way, that all what I need to do to have this bilinear term, well, for the left-hand side, shown in the first equation, I just need to push this operator over here. And then for the two off-diagonal terms, I just actually to push only one operator because they are symmetric. One is the transpose of another, and by just setting this true flag over here, I make sure that both of the off-diagonal blocks of the matrix will be filled, will be assembled. And finally, the source term on the right-hand side is also being taken care of by pushing the appropriate operator now to the right-hand side. Yes, maybe you can notice that the previous three terms that we considered were for the left-hand side of the equations, and that's why we have here something called left-hand side pipeline. And now this source F is something which will be on the right-hand side, and that's why we have here this right-hand side pipeline. So we try to be consistent with all this naming to make adding equations as easy as possible. Having done that, I want also to stop very quickly and not really on the code. I think like what I'm showing on the left-hand side of the slide is more important. I just wanted to highlight what are the norms of the errors and error indicators we're going to be computing. So the L2 norm is the norm of the difference between the solution, the finite element solution and the exact solution. And then we're going to call by H1 semi-norm. This would be the L2 norm of the gradient of the solution. Yeah, different between the gradient of the finite element solution and gradient on the analytical solution, the exact one. And finally, the local error indicator, as I mentioned before, is something which is computed on a posteriori on the two fields that are solved monolithically in our system, the gradient, the field U, and the field flux Q. So the norm of the difference between them will going to give us the error indicator. And just on the right-hand side of the slide, I'm just showing that each of those norms is computed by a couple lines of the code. So why we are looking into those indicators, those a posteriori error indicators? The idea is that we don't want just to compute them after we solve the problem. We want we want to make some decisions of how to do the refinement based on the values of the error indicators. And on the right-hand side, you see the pseudocode of this refinement loop. And we're going to continue doing this loop until the total value of the error indicator. We're going to continue doing the loop while the total value of the error indicator is greater than user-specified tolerance. And at each step of this refinement loop, we're going to be doing the refining. And then I want to be clear here what kind of refining I'm going to be talking about, because there are different ways of how people can do refinement. Yeah, you can do H refinement when we divide elements into smaller ones. We can do p-refinement when we increase the order of approximation functions. And this is exactly what we're going to be doing in this example and in the hands-on sessions as well. HP refinement, something I'm going to mention in the passing, is the combination of the H refinement and P refinement. And then there are also some even more exotic approaches to refinement, something called our refinement when we relocate positions of the nodes. And this is something particularly useful in problems related to fracture. Perhaps some of you have heard about so-called quarter point element. So where the nodes are shifted towards the tip of the crack to improve the approximation of the singularity of the stress there. But it's not something we're going to look at. We're going to look into the p-refinement. And here's just an idea of the implementation of the refinement. And again, if you're not enjoying looking at the code right now, don't focus on the right-hand side. This is there just for the reference because we're going to be sharing the slides with everyone, and I wanted some of the things to be written on them. What's more important is on the left-hand side is that how we actually going to do the refinement. Yeah, because like we discussed how we're going to compute the error indicators, but we discussed how we're going to do the refinement, like what we are actually going to do. We're going to increase the orders, but where to do it? We need some criterion to decide which elements to refine. So this is very classic approach to defining this criterion, which I found in Mike Answorth's paper. We will refine the elements where the error is greater than the maximum error from all the elements in the mesh multiplied by some parameter theta. And typical theta is between 0 and 1. And one of the tasks in the hands-on session today for you would be to find out the optimal value of the theta, which would give you the most effective refinement possible. And now that when we do this check for all the elements in the mesh, we check if we need to refine them or not. We're going to we create the collection of the elements, some kind of container which holds the ones which needs to be refined. And then, as you can see, the refinement, p-refinement itself is very easy in our code because we just need 2 lines. We just bump up the order from p+1 to p+2 for the flux and for the field Q, and from p to p+1 for the field U. Okay, I promised that this is the last piece of the code I was showing, and now we're going to look at the results a little bit to the problem that we considered. Remember that we had this problem, the Poisson problem in the square domain with a known analytical function, and something I want to stop first is the looking into the a priori error estimates. Because before we go to this p-refinement and a posteriori error estimates, I wanted to stop on the a priori error estimates. The a priori error estimates are the ones that we know that they are they hold for the finite element problem even before we solve the problem. Like for example, that we know something over here is that we know that the L2 error of the finite element solution should decrease as the element size to the power of p+1, where the p is the order for U. On this plot, in this figure, I am showing the convergence of the L2 error, L2 norm of the error with the decreasing element size for different orders. Yeah, so the purple one is for the order 1, the cyan one is for the 2, and so forth. And now with the dashed lines, I'm showing the standard finite element formulation for Poisson, the ones that I mentioned in the beginning, where we have just one field U in H1. With the full lines, I'm showing the convergence of the mixed formulation. And as you can see, they are parallel, meaning that our implementation is at least as good as the standard one. And if you carefully look at the slope, you will see that, for example, the slope of this red one over here is 5. Yes, so that we go from 10 to the power minus 6 to something like 10 to the power minus 11, and while the H drops by 10. So we decreased 5 orders, 5 order magnitude of the error when we decrease the element size by just by 10. So that means that the slope is 5. Which is the case because for this red curve p equals to 4, so our a priori error estimates hold. We can do this also for the for the H1 semi-norm, for the norm of the difference between the gradient of the solution, finite element solution and the exact solution. And here, again, our mixed one and standard one are parallel. And the a priori error estimates, which we know from the beginning we should hold, says that in this case, the error of the gradient should be decreasing as element size to the power p. And that's exactly what you will see over here, that the slope of this line is 4. Yeah, so the error drops from 10 to power minus 3 to 10 to power minus 7. So 4 orders of magnitude when the h is decreased 10 times. So, okay, at least it's working, but this is just a small part of the picture, because that's just a proof that the implementation is correct. But something we want to see is to check the optimality. So how the error is decreasing with the increasing number of degrees of freedom. And here, on the first glance, it looks that the mixed formulation is actually a bit worse than the standard formulation. Yeah, like if we look into this plot, and okay, let's just compare these 2 points over here. So again, the full curve, the full line is for the mixed formulation. The dashed one is for the standard. And here we are reaching the same error of 10 to power minus 11, but the standard one actually requires 3 times less degrees of freedom. Yeah, so if we increase the order of approximation everywhere in the domain, and if we refine the whole domain, so we do the global refinement, both H and P, well, in this case, since we have those additional degrees of freedom for the flux, the standard one is better. But this was not the point in defining the mixed in the first place for the global refinement. The whole goal of mixed formulation is to enable the adaptive refinement. And this is what we're going to come in the next slides. So, but before that, I wanted to show you how these errors and error norms and error indicators look on the domain. So on the left-hand side, this is the error L2 norm. That's the difference between the finite element solution and the exact solution. In the center, we have the difference between the gradient of the finite element solution and gradient of analytical solution. And on the right-hand side is our error indicator computed from these 2 fields that we found out. And first of all, we can see that it's clear that the same elements are highlighted. So the error indicator is indicating the right elements where the real error is high. But also we can see that, okay, the values of the error indicator themselves are different from the L2 norm. But if you look carefully into the values between this one and this one, you will see that they're almost the same. Actually, if you look into this right-hand side, you can see that the maximum value for the error indicator is just a little bit smaller than the real norm of the error. Yeah, it's 7.1 to 10 to power minus 5 and 7.2 to 10 to power minus 5. It's just a bit below. And what this shows is that our indicator is not the strict mathematical bound. Yeah, because like it doesn't, it's a bit smaller than the error itself. But this was not our point. We didn't want to have a strict mathematical bound. We wanted to have a good indicator. And I think like for this particular case, it is really good enough. Okay, so and then if we just for each refinement step, if we look into those elements highlighted by the error indicator and do the refinement on them, we will see how the orders are increasing on the left-hand side of the slide, and we can see how the error norm is dropping on the right-hand side. Yeah, so at the beginning, it starts from the values of like 10 to power minus 6 on in each individual element. And then when we get to the order 10, the error will drop, as you can see over here, to 10 to power minus 20, or even further, 24. So it's working effectively. And then if we now compare the standard solution to the Poisson problem with our mixed with adaptive p-refinement, we can see the big benefit. Yeah, so the curve with the different colors here correspond to the different orders of the standard mixed formulation, so a standard formulation for the Poisson problem, and the black curve with circles correspond to this now adaptive p-refinement. And actually those circles correspond to each individual step of the refinement. And so that was I was mentioning, that the number of those steps will depend on this parameter theta. And this was what I was mentioning regarding the hands-on session, that we would ask you to play with this parameter theta to find out how can you get to this kind of error, this 10 to the power minus 7, as quickly as possible. And so the last thing I ask you to look here is to compare those 2 points. So we get below the error of 10 to the power minus 7. This was our tolerance. But look that what happened, that the standard one got there in something like 8 to 10 to the power 5 degrees of freedom, while the adaptive p-refinement for the mixed formulation got to the same little error in something like 4 to the power 10 to the power 4. So we have 20 times less degrees of freedom for the mixed. And this is the real benefit of this formulation, that we can reduce the number of unknowns with the same accuracy by 20 times. So I hope this now shows the real motivation for what we are doing over here, why there's so much emphasis on the mixed formulations. But I also want to highlight that this was a very simple example, and the algorithm that I was implemented is like a very straightforward and simple one. It only does the p-refinement. If you do HP refinement and if you use some more sophisticated criterions for refining the elements, we could be even more effective. And actually, we have another more advanced tutorial in WOFM. If you're interested in that, we can have a quick chat later on about that, where we can combine H and combine H and P refinement. And by doing that, we can get something called exponential convergence for the similar kind of problems. But I don't want to stop on that for a long time. I now want to get to the actual to the actual topic stated in the title of this talk. So in the last 10 minutes of my presentation, I want to talk about thermoelasticity and explain how the things that I just described are playing a role there. So give me 1 second to get a sip of water. Sorry. Okay, so since what we were looking into previously was very mathematical, here we're going to switch to something a bit more physical. We're going to talk about thermoelastic coupling, and we're going to see how the mixed formulation can improve the solution for this coupled problem. We need to fix ideas about what we're going to call thermoelastic coupling, a thermoelastic problem here, because there could be different ways of looking at it, one-way and two-way. So we're going to be focusing on a one-way coupling, which is also sometimes called linear thermoelasticity. And I think there was a very good question in the Q&A earlier today during Ignatius's talk about what happens when you consider this mixed formulation. So the truth is that you can have coupling, but your problem can still be linear, as in it will be solved by one step of Newton-Raphson, because your left-hand side, your tangent matrix, your left-hand side matrix is constant. So in one-way coupling, we see that the body experiences expansion or contraction due to temperature change, and therefore the actual stresses depends on thermal strains. But we do not consider in this one-way coupling how the temperature would change because of the strain itself. So this kind of coupling can be represented by this formula over here, where we can see how the actual stress on the left is computed from the actual strain and the thermal strain. Yeah. So the second term inside of the brackets is the thermal strain, and both terms inside of the brackets give you something called mechanical strain. And to my taste, the thermoelastic problem description like this is mathematically correct, but it's a bit cumbersome, while the problem seems to be very simple itself. And therefore, I think this drawing on the right could help understanding the meaning of this formula on the left. So just imagine a bar which is fixed on both sides, so it cannot actually expand. But then you consider the thermoelasticity and you start to heat up your bar. Well, you know that it's not going to, and there's going to be no deformation. Let's assume that there is no Poisson ratio is 0, so there is no expansion in the vertical direction, but there cannot be any expansion in the horizontal direction. So the actual strains the one which satisfy the boundary conditions, the admissible ones, are 0. But we know that if we are heating up this bar, it wants to extend. So there is something called thermal strain. It's not a real one. It's kind of a virtual one because it doesn't happen, but the body wants to do it. It wants to expand, as it's shown over here. So yeah, like I said, it's virtual. It doesn't really happen. So there is a mechanical strain, which is kind of pushing the body together. So like it's as if there was no boundary around hand side, and the body extended, and then someone pushed it back to actually satisfy the boundary condition to have the displacement for the displacement to be admissible. And now you can see hopefully that the mechanical strain is the difference between the actual strain and the thermal strain, and that the actual strains, the ones that you can measure, the ones that give it traction, are the ones which can be computed from the mechanical strain using the elasticity tensor. And so here, just to explain notation, the alpha is the thermal expansion coefficient, which we can consider to be isotropic for the purpose of this lecture. And then, of course, T minus T0 is the change of temperature, and like I said, is elasticity tensor. Okay, so this is the formula we're going to use. And then just to give you a hint that the two-way coupling is the case when we have the actual stresses depending on thermal strains. So the actual stress depending on thermal strains, like in the one-way coupling, but also temperature depending on the actual strains. For example, due to the change of density. But this is not something that we're going to talk about. Okay, let's just jump in on the equations for this case. So we have our balance of linear momentum for the stress tensor sigma. We have our heat conduction equation for the temperature field T, where K is the conductivity and C is volumetric heat capacity. And we have here the time derivative of the temperature. We need to set up the boundary conditions. So on the right-hand side, please do not consider it as two bodies. This is not the case. This is the same body. It's just that we need to set up the boundary conditions for the thermal part and for the elastic part. And so we have the Dirichlet boundary conditions probably on some different parts of the mesh. They don't need to be. They can overlap, or they don't have to overlap for the displacement and temperature. And then we have Neumann boundary conditions on the remaining parts of the boundary of our bodies, where we prescribe traction and the heat flux. And of course, we also need to have the initial boundary initial condition for the temperature to solve for the time-dependent problem. Okay, so the standard weak form, something which is kind of a combination of what I was showing before for the Poisson problem with regards now to the heat conduction, and also combined with what Ignatius was presenting for the weak form for this solid elasticity. So I'm not going to spend too much time on this. You can refer back to the previous lecture, but the idea is that we're looking for the H1 field for the displacement and H1 field for the temperature. And we have the two equations for those two fields. And in this case, we have that we see that the Neumann boundary condition for the traction is manifested as natural BC over here, and the Neumann boundary condition for the heat flux is also manifested as the natural boundary condition, while the Dirichlet boundary conditions are as usual as the essential boundary conditions. Okay, so this is standard. Now let's look what's going to happen with the mixed form. The strong form on the left doesn't change much. It's just that we introduce our flux. So I mentioned before that in the Poisson problem, we had that the flux was just the gradient of U. But here we need to consider actually the Fourier law of the heat transfer. Therefore, our flux is minus K gradient of temperature. But except for that, everything else stays the same. Yeah, we have the Dirichlet boundary conditions for the displacement and temperature. We have Neumann boundary conditions for the traction and heat flux. But we're going to consider now the weak form. But the weak form is going to be only for the thermal part. the elastic part is going to stay in the standard form where displacements are in H1 field. Just a little side note over here is that in the Lucas's lecture tomorrow, you will see a case where even this this assumption is dropped, and you would look for the displacement in L2 field. But for the moment, it's not what we're doing. For our elastic problem is as it is standard, it's the thermal problem which becomes weak. And therefore, the flux in HDF and temperatures in L2, we have now 3 equations. And the same trick, as I was mentioning about the boundary conditions, happens here as well. Yeah. So if we consider the boundary condition for traction, those are Neumann boundary conditions. And like I said, the elastic problem is solved here in the standard variation approach. So those conditions are manifested as natural. But if we look into this term over here, we can see that we have a natural boundary condition, but the prescribed value is not for the flux, it's for the temperature. And therefore, this is again the case where the Dirichlet boundary condition is manifested as natural because of the mixed formulation. And then in this case, the displacement boundary conditions are essential as usual because we use the standard for elasticity. But please note that the Neumann boundary condition for the flux becomes essential boundary condition for the Q. Because this all makes sense now because the Q is HDF space. And that's why it makes sense to prescribe the values of HDF space, actually the normal components of the functions from HDF space on this boundary gamma Q, where we have the prescribed flux QM. Okay, I hope this makes sense. And the last thing that I wanted to show you is just to look into the example. And this is the problem where we're gonna be solving this thermo-elasticity. And the problem is constructed in a way that we have low regularity of the solution. I will explain in a second what that means. But the problem is as follows. We have a plate, a square plate with a circular hole in the middle. And this plate is made from 2 materials. Yeah, so there is material 1 and material 2. And the difference of this material is drastic. The Young's modulus of the material 1 is 100 times higher than the Young's modulus for the material 2. And the conductivity for the material 1 is 10 to power 4 greater than the conductivity for the material 2. Yeah, so like material 1 here is hard and conducts heat very well, while material 2 over here is soft and doesn't conduct material very well. Doesn't conduct heat very well. So the boundary condition that we consider here is that we have the temperature 0 equal to 0 prescribed on those 2 edges, and then we have very high temperature prescribed at the surface of the hole. So the way how you can see it is that initially the temperature is 0 everywhere, and it stays 0 at the top and right hand side, but we have kind of a flash heating inside of the hole where the temperature jumps to 1000 immediately. And obviously this problem has a symmetry, so we're going to be solving only for a square of the domain. And we're going to solve for like the 50 time steps, and we're going to look into the solutions in the whole domain, but also we really want to look into what's going to be happening at this point of interest that I highlighted with the star next to the boundary between those 2 materials. And why this is the particular interest for us is because of the benefits which mixed formulation is going to bring. Because this is the case where we're talking about the low regularity of the solution. And this low regularity of the solution is dictated by this jump in the conductivities that I mentioned before, that for the material 2, the conductivity is 10,000 times greater, 10 times lower than for the material 1. So we have a discontinuous conductivity, and therefore, if we consider the exact solution for temperature, we should it should have a king. Yeah, I'm talking now about the exact solution, which is unattainable, of course, because this is a problem which is very hard to find the analytical solution in a closed form. But we know that the temperature is something which is continuous in nature, because of the continuity of the material, the conservation of energy. Temperature should not be actually jumping in the matter. But it can have kinks. It have very, very, very nice and sharp gradients, as I was showing over here, where it's changing from 0 to 1000. So how are we going to approximate that? Well, if we go with approximation L2, which is provided by a mixed approximation, we can have on one element value of 1000 and another element value of 0, as shown over here. Please note that we're going to define our mesh, that this boundary between the regions is happening at a node. So since we are not interested in the values exactly at the node, we are with the finite elements, we are always interested in the values at the integration points, which are some distance from the node, normally, at least for Gauss integration. This formulation is going to work perfectly. Yeah, we're going to have this discontinuous approximation in L2 space, where we have one value for this element and this value for another element. And we are not even trying to describe the jump between the two. So this is valid. This is not a problem at all. The conservation laws are fulfilled because we have this divergence of Q term, which ensures that the fluxes are continuous. So energy-wise, everything is fine. It's just that our approximation looks like this. And now let's compare this to the case where you would look into the H1 approximation, which has to be continuous. Well, it cannot afford the standard one. It cannot afford to have this kind of kink. It will always try to have something continuous, and at best, it will do something like this. So there's going to be a considerable error between the numerical approximation and the exact the solution shown in the blue dashed curve. But this is something. Okay, you can try to improve this, of course, with refining the mesh. If we increase the number of nodes by 2 times, probably we could expect that this this inclined part between the two regions will be smaller in length. But this is something a bit idealistic, and this is gonna be happen like this only for the very small jumps of the parameters. What you're gonna see in reality for the case we are considering over here is that the solution is going to behave something like this. You're going to have an instability, which is going to propagate into the region with the constant values of the parameters. And this is not good at all. Okay, so I'm going to, in the last couple of minutes, I'm just going to show how the solution looks like. So I'm not going to show it time dependent. We're not really interested into how things are changing here in time. What we're interested in how they're changing in the domain. So I'm showing the solution for this quarter of this plate. Here, the mesh was warped by the displacement and magnified by 50 times. So this is something that you're going to look into yourself in the hands-on session in the afternoon. And I'm showing here the displacement magnitude between the standard formulation and mixed. You can see that it's almost the same. Probably there is a little bit of difference in this band in between the elements, in between the regions with different properties, but it's not that noticeable. Overall, displacement field looks okay. But if you look into the temperature field, there is a huge difference between the standard and mixed formulations. So the standard one, so the mixed one is very carefully showing us how the temperature is changing by something close to 1000 to something close to 0 in the boundary between the regions. While the standard formulation is trying to do exactly what I mentioned. It tries to have something continuous, approximation of the temperature, and it cannot do it for this set of the parameters. It has a kink. It has a jump and it has an instability. And you can see that there is a layer of elements, actually layer of nodes, where we have significantly high values in the negative range, which is this manifestation of this instability. We can look into this. So like previously, I was warping in 2D by the displacement, but here I am warping in a third direction by the temperature itself. Yeah, so not only the color now shows the temperature, it's also the height with how the mesh is visualized over here, showing the temperature. And here you can see the difference between the standard formulation and the mixed formulation. So the mixed formulation is exactly doing what I was mentioning, that there is a jump between those two approximations in L2, approximation for L2 and this element, and approximation L2 and this element over here, and that's why we can represent this difference in the temperatures coming from the fact that we have very different materials very carefully. While in a standard formulation, you can see what is happening. It's exactly that case of the inclined curve jumping up and down. Of course, you can do the convergence terms of this. So like the point of interest that I was showing, those stars, is somewhere over here. And this is something that I didn't include in the slides, but I included into the hands-on session in the afternoon, where you would look into how the convergence looks like and how it is much, much better for the mixed formulation compared to standard formulation because of those instabilities that you see on the left. Sorry for being a bit off the time. I'm done with this. So hopefully this presentation was helpful to understand the new benefits coming from the mixed formulation. If you have any quick questions,